Every time you swipe a credit card, a machine learning model makes a decision. In data science, predicting a continuous number, like the exact price of a house, is called regression. But deciding whether a transaction is legitimate or fraudulent is a problem of classification. The machine has to force the data into distinct categories, normal or fraud. In this dataset of 100,000 transactions, 99,000 are normal, and only 1,000, the red dots, are fraud. If an algorithm blindly predicts normal for everything, labeling the dataset green, it achieves 99% accuracy. But 99% accuracy doesn't mean the system works. By blindly guessing normal, the model missed 100% of the actual crimes. The most critical events in the real world, a hacked account, a failing hard drive, a rare disease, make up the smallest fraction of the data. Relying purely on top-level accuracy leaves us blind to complete algorithmic failure. This chart shows a standard linear regression trying to map those binary outcomes. Using a straight line to separate fraud from not fraud fails because the math eventually predicts impossible probabilities, values dropping below 0% or extending above 100%. To fix this, data scientists use logistic regression. By applying a mathematical formula called the sigmoid function, they contort that rigid straight line into an S-curve, strictly bounding the predictions between 0 and 1. With the probability boundary drawn, simple accuracy no longer tells the full story. We have to adopt a new framework to expose exactly how the machine is failing. Here we have a confusion matrix. It breaks down algorithmic errors into 4 distinct quadrants, mapping what the model predicted against what actually happened. The false positive quadrant represents innocent customers wrongly accused of fraud. We measure this specific error rate using a metric called precision. Low precision means you are freezing legitimate bank accounts and alienating users. The false negative quadrant tracks the actual criminals slipping through the cracks. We measure this with recall. Low recall means the model is ignoring the exact threat it was built to stop. You rarely get high precision and high recall at the same time. Tuning a model to catch more fraud usually triggers more false alarms. To evaluate the compromise between these two competing metrics, we calculate their harmonic mean, producing a single number known as the F1 score. True model performance is a calculated balancing act. You are constantly weighing the cost of inconveniencing the innocent against the danger of missing the guilty. Even with a perfectly tuned F1 score, a model cannot learn to catch fraud if it is starved of examples. That 99-to-1 imbalance guarantees the machine won't recognize the pattern of a crime. Standard fixes usually introduce new problems. Randomly deleting normal transactions destroys valuable baseline data, while endlessly duplicating the few fraud examples causes the algorithm to memorize exact copies rather than learning the general threat. Look closely at this visualization of our training data. The sparse red points represent our few known fraud cases, swallowed by the green majority. To balance the scales without causing memorization, we use a technique called SMOTE. SMOTE looks at the closest neighboring fraud points, draws geometric lines between them, and hallucinates mathematically plausible, entirely new data points along those vectors. By fabricating a balanced reality strictly inside the training environment, we force the algorithm to finally recognize the true shape and density of the threat. Credit card fraud is a classic binary problem, but real-world data takes many forms, requiring different mathematical architectures to handle specific types of categorical evidence. Classifying an SMS as spam or ham relies on naive Bayes. It assumes every word, like lottery or free, is independent, then calculates the probability of spam based on how often those words appeared in historical samples. For data that is spatially tangled, support vector machines find the optimal hyperplane. They maximize the margin, the empty space between classes, effectively carving a wide neutral zone between the groups to ensure a clean separation. When logic is hierarchical, we use decision trees. They ask a series of questions to find the most decisive features, measuring the impurity of each bucket to ensure every branch leads to a clear, concentrated outcome. Whether the machine is calculating probability, carving space, or branching logic, its success is completely dictated by the raw, often imbalanced reality of the data it consumes. Drawing a strict mathematical boundary is the starting point, but the final choice belongs to the data scientist. By selecting a target metric like recall or precision, we determine exactly which errors we are willing to accept and which ones we must eliminate.